So let's start off our discussion on fluids. So here's typical sorts of diagrams that you might see of fluids, either oil or soap in this case, showing the kind of flow you might see in a more complex case. Or here, two interacting turbulent vortices and the sort of ordered flow that occurs between these vortices. We are going to deal with slightly simpler definitions of fluids and how they behave. Of course, something else that can behave as a fluid tends to be cats. But we'll stray away from pouring mammals into vials and moving them through tubes and stick to such things usually as water or perhaps gases. So, before we start, let's define what sort of things can behave as a fluid. So there are four basic states of matter: solid, liquid, gas, or another, which is plasma, which is really a subset of a gas. A solid has a definite volume and shape, and maintains that shape and size unless exhibited to very large forces. A liquid, as we should be familiar with, has some definite volume and flows, but does not have an overall shape of its own. It tends to take the shape of its container. Gas, again, expands to fill its container and take the shape of that container, but doesn't have a definite volume or definite shape to it. It really fills up whatever volume you provide. A plasma, as said before, is kind of a subset of a gas. It's a gas that consists of ionized atoms, the electrons being stripped away, and is in a state of very high energy. This tends to flow, as do gases and liquids. Solids, unless under very, very extreme situations, such as massive asteroid impacts on planets, tend to behave as solids and not flow. So when we're talking about our states of matter, solids tend to occur at relatively low temperatures, such as the ice cube here, melt into liquids, become gases, and then finally plasmas as the temperature increases. So a single material can be in any one of these four states, depending on how much energy is provided to it. Something to recall, and we'll deal with this in more detail when we talk about thermal physics, is that the temperature of a system is really the average kinetic energy that's available to the particles in that system. The more energy that's available, the more heat you apply to a system, the more the particles in that system will move around. So thermal energy is a measure of the kinetic energy of the collection of particles. The higher temperature, the more energy per particle. The more kinetic energy, the more the gas or liquid will move around. So in terms of our states of matter that we previously talked about, we can also look at these in terms of energy rather than just temperature. Solids, liquids, gases, and plasmas. Here we consider solid in a nice ordered lattice. As we provide more temperature, more energy per molecule, the actual particles making up this lattice work start to move around and have more degrees of freedom and move over one another, begin to flow. They then get enough energy to start discorporating from one another and being in a looser association, such as a gas, and then, once they become totally electrified and ionized, can show themselves as a plasma. So fluids. Fluids have an ability that solids lack. Fluids have the ability to flow. They're basically a collection of molecules that are rather randomly arranged and are held together by cohesive forces which are a little weak. They can also be held in place by the walls of a container. So pour liquid into a can or into a bottle or flask, and it will fill up that container and be held within it by the force from the walls of that container. A solid will maintain some kind of constant shape. Something like a brick tends to not change shape too easily. A fluid, as we said, will flow. Here is the fluid filling up this container, and a gas or a liquid can actually expand to fill up their container entirely. There are some materials, of course, that are solids, but actually fall into the category of fluids. If you look at very, very old houses with ancient glass in them, that glass has seeped and has become thicker at the bottom than it is at the top. Glass itself is actually a fluid. It's just moving very, very, very slowly. So we see it really as a solid. Asphalt is actually a fluid, but it flows very slowly again. And you can actually see in very, very high temperatures, roads can actually melt. Another case is also plastics. Some of these are actually fluids, but we use them and utilize them as solids. So there are two categories of fluid mechanics that we're going to look at. There's fluid statics. This is the behavior of fluids at rest, say just sitting in their container, and fluid dynamics. This is how fluids move, how they behave when they're in motion, and the various effects that come about from their motion. Now, we're not learning any new physics here in terms of mechanics, we're just applying it to fluids. So Newton's laws will apply in all of the situations we'll look at, as they have for all of basic mechanics. But first of all, we really need to categorize some of the basic definitions that we have in terms of a fluid. So let's take a look at the density of a fluid. Density can be referred to as the average molecular spacing in your substance. If you take something like a liquid, the particles are spaced out more widely than they are in a solid. And in a gas, the particles are once again even more loosely bound and even further apart. So a gas has less density than a liquid, which has less density than a solid. Density tends to be given by the equation ρ for density is m over v. So ρ represents density, m represents the mass, and v represents the volume that your material is occupying. So density is m over v in kilogram per meters cubed. It can be expressed in grams per centimeter cubed, but for this class we'll try to keep ourselves in the realm of SI units of kilograms and meters. There is a variation of density with temperature. As we heat up an object, it will expand, and that expansion will mean the particles get further apart. So while the mass of an object can stay the same, if its volume increases, its density will reduce. So take, say, a can filled with a fluid. If you actually heat that can up and the can expands as it would, then the density of that fluid may be reduced. So we can use the density quite often to find the mass of our fluid. So ρ is m over v, m can be ρ times v. Something to keep in mind is there is a difference between the mass of our fluid, the mass of what we're looking at, and its overall weight. Remember, a weight is a force due to gravity. Anywhere we see a weight means we have to take our mass and multiply by a factor of 9.8 meters per second, mg. So m times g is equal to ρ v times g. Typical densities, m over v, there's something we call the specific gravity, which is a density relative to that of water. So a specific gravity here can take any value relative to water. The density of water is 10 to the 3 kilograms per cubic meter. And here's some typical densities that you might see. Density of air, 1.29 times 1.29 kilograms per cubic meter. And as you can see, these start to change drastically. So air is a gas at 1.29 kilograms of material every cubic meter. Something like aluminium, there should be an I in it in my particular case, is 2.7 times 10 to the 3. So we're looking at orders of magnitude greater here for metals and solids than we see with a gas like air. Contrast that with helium and hydrogen, very light, rarefied gases, which are looking at about 2 times 10 to the negative 1 or 9 times 10 to the minus 2 kilograms per cubic meter in the case of hydrogen compared to air. So as I briefly touched on in the previous slides, specific gravity is a relative density. This is the ratio of the density of a substance to that of water. This just gives a good baseline from which we can measure our densities. And water, being the ubiquitous material that it is, tends to be the one that gets chosen as the baseline to a lot of things. So the density of water is 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. So as we said before, densities often depend on temperatures and pressures. The specific gravity always refers to that relative density that's quoted, and the ratio of density to the density of water at some 4 degrees Celsius standard. Most of the time, I'll try to provide you with a density, but a specific gravity is often quoted in problems. So as we said before, Newton's laws still apply to everything we do. And in fluid dynamics, we're going to utilize Newton's laws. There are a few differences, though, in the way that fluids behave compared to solids. In terms of static fluids standing still, they don't sustain stresses, shearing forces very well, and they tend to be exerted parallel to the fluid surfaces. This will be clearer as we look at a diagram later on. Static fluids also don't sustain tensile forces, and again, the forces tend to be perpendicular now to the fluid surface. This means that because of these properties, what this is really saying is fluids will tend to be influenced by their container and essentially take the shape of their container and flow through a pipe or container in the same shape as that particular vessel. So only the force that's exerted on an object that's submerged in a static fluid will give you a compression on all sides. So the force that's exerted by a static fluid on an object is always 90 degrees to the surface of the object. So what we're saying is, if we look at a great big column of, say, water here, if we look at a parcel of that water and how much force is exerted on it, F in this case, it will be exerted over some area. So the pressure at some point in a large vessel of water will be P is F over A. That force is just 90 degrees due to the weight of water. Now, if we're looking at pressure, the units of pressure that we use in the SI system are pascals. There are a lot of different pressure units, as we'll see shortly. But 1 Newton per square meter is 1 pascal. And this should make sense from this equation. If P is in pascals, F is in newtons, A is in meters. Well, square meters, because it is an area. One side multiplied by the other. And this is really the effect of saying how forces interact with our fluid. If we pour a fluid into this bottle, we will end up with it assuming the same shape as the bottle. Because the pressure is 90 degrees on any fluid due to the solid surface, we will end up with forces acting like this. The force from this bottle will restrict its movement, so we'll have a force in this direction and we'll have a force in this direction. Something to remember is pressure itself is a scalar quantity, whereas force is a vector. So that means we have to somehow find a vector quantity from a scalar. Pressure is proportional to the magnitude of the force. Proportional, they're not the same. Pressure is basically force divided by an area. Now, the reason you end up with a scalar coming out of that is because when you divide force by an area, what you're going to end up with is something that's only in terms of newtons. So here P is equal to FA. Our pressure is a force acting on this area here. So pressure is acting, and we said always at 90 degrees, from every direction on this particular object that is down submerged in our container. This will mean there is a force per unit area on every face of the cube. Because the pressures applied to any part of this fluid is transmitted to it from the fluid's container, the walls of this container are what's providing the force. If the container is all around, then the pressure should be the same on each face. You'll end up with the same force. The pressure will be the same because the area of this cube is the same on each face. Now, something we know, if you study such things as deep sea diving or have jumped into a pool and gone to the bottom, is you'll find that there's more pressure the deeper you go into your fluid. So pressure actually increases with depth. So if we actually look at this particular problem here we have a jar and we're putting a cylindrical parcel of fluid into this jar. As we put it in, as the depth increases, we will have a component of gravity, negative mg, and this will be the force that's acting on this. We will have an area to our cylinder, and this pressure will increase as this cylinder goes deeper and deeper into this jar. So three forces will be acting on our cylinder as it moves into this liquid. Downward force will be equal to P0A here on this face, an upwards force, which is going to be equal to PA, and gravity, negative mg. If we want to find m, we can say, well, this is going to be rho, our density, times the volume. Our volume here is going to be A times H. What is the area and what is the height? So the sum of all our forces will be PA, this is the upwards force, minus the downwards force, minus the force due to gravity. If the cylinder is standing still here, all of our forces should be equal. So F will end up being equal to 0. If we solve this in terms of P, we can cancel out the A's here, and we can end up with an equation in terms of just P. So the pressure will be equal to P0. What is the pressure here at the surface? Plus rho GH. So P0 is the surface pressure, rho GH is the pressure further down. So if we wanted to find a pressure at some height, we'd take the surface pressure and then we would add rho times G times H, dependence of the density of the fluid, the gravity, and how submerged it is. What is its height within the fluid? So P0 tends to be the atmospheric pressure in most cases when your object is not submerged. So if we take a closer look at this in a slightly simpler diagram here, here's our object, here's the force due to gravity, you should always write that in first, the mass times gravity, PA acting upwards, and the atmospheric pressure times area acting downwards. W is going to be our weight. This is equal to mg. We can then substitute in for m with rho v. If we substitute for volume, volume is going to be the area, the cross-sectional area of this, multiplied by its height. So we're substituting again for v here. So weight is mg, substituting for m gives us rho V. Substituting V gives us rho AHG. As we said before, our sum of our forces is going to come to 0. This means PA, the upwards force, minus P0A, the downwards force, minus the weight, is equal to 0. That gives us A in both of these cases. And this is the same area. So factoring out A gives us P0, the atmospheric pressure in this case, plus rho GH. And this is an important result to remember, and you're going to use this quite frequently. So you can see this in two forms here, P0 plus rho GH or P0 plus rho G delta H. This change in H essentially would be how deep your object is. In this case, there's going to be a difference in the pressure at the top and bottom of this cylinder based on this height. And this is an equation definitely that you should keep in mind. So let's look at an example that uses this equation. So here we have a situation where we have a water tank here at the top of a cliff, precariously balanced over this house. I really wouldn't want to live here with this weight of water right above my house. I'm sure these people can't get insured. But anyway, this is a physics example, and rarely are they wise things to be doing with pressures, forces, and large weights of water. So the question here is, at what pressure will water exit the pipe into the house? So here's our tank, here's our pipe running into the house, and we have a height differential here of 30 meters from the top of the water to the pipe going into the house. There are a few things we will have to consider before we can even start this problem. If you think about the previous equation, we needed a few things to make this happen. One of the things you'll definitely need will be the density of water, rho H2O, which is 1 times 10 to the 3 kilogram per cubic meter. G, the acceleration due to gravity, the one value I expect everyone in my physics courses to always just know and will never be provided on a formula sheet. G is 9.8 meters per second, and a height of 30 meters taken from the question. So you're not presented with a lot of data when you look at a problem like this, and you have to go to a few standard definitions to make this work. If we think about our equation, delta P was rho GH, where rho is now that of water, rho H2O, and now we can substitute in. So delta P will be 1 times 10 to the 3 kilograms per cubic meter times 9.8 meters per second times our height of 30 meters. That will give us a final answer of 2.94 times 10 to the 5 newtons per square meter. Remember, a newton per square meter is indeed a Pascal. So let's take a look at a slight variation on that same problem. In the previous case, we were very lucky. Everything was in straight lines and oriented with the y-axis just falling straight down the pipe. In this case, we have a water tower at a height of 5 meters. We then have a slope of 110 meters at a 58-degree angle for the pipe to run into the house. A question again, at what pressure will water be ejected from a broken pipe at the bottom of the hill? So what pressure will water fly out of this pipe and into this house if it breaks? Well, what do we know? It's always best to make these sort of shopping lists. We want to find pressure, but the tank depth is 5 meters, the pipe length 110, and the slope 58 degrees. One of the things we do have to calculate here is what is the total height of the water. And this isn't really so much a problem involving pressure, it is a bit of trigonometric wrangling. So we already have 5 meters at the top, and now we have to figure out what is the vertical component here. How high is our water? So our height is going to be 5 meters plus 110 meters, and if you figure out the triangle here, which you should always go back to your basic trig, sine of 58 degrees. So 5 plus 110 sine 58 will give you 98.3 meters in height. This diagram is obviously not to scale. Now we can go back to our previous equation. P is going to be rho GH. Rho we had in our previous question of 1 times 10 to the 3 kilograms per cubic meter for water. G is 9.8 and our H is 98.3 meters. That'll give us a value of 9.6 times 10 to the 5 newtons per meter squared, or 9.6 times 10 to the 5 pascals. I'm unconcerned about how you quote this final unit. I'm happy with newtons per meter squared. I think it's quite descriptive and tells you how much force you're getting per square meter. But the pascal is just as useful. You don't just apply this in terms of fluids moving in a pipe. You can also look at things like atmospheric pressure. Earth's atmosphere is actually a fluid. There's no real fixed surface to that fluid, though. What tends to happen is the atmosphere gets more and more rarefied as you go higher and higher until you're eventually in the vacuum of space, where particles are more of a rarity. A change in height, in this case, instead of being the top and bottom of a hill, will be our delta H, should be our altitude in the atmosphere, so delta P is still rho G delta H. When we are talking about different heights above Earth's surface, either down into the ocean or up into space or up into the more rarefied atmosphere, say at the top of a mountain or at an aircraft altitude, then we often refer to pressure at sea level, and that tends to be our P0 value. And a lot of pressures are quoted relative to sea level. And P0 is 1.013 times 10 to the 5 newtons per square meter. You often also see this given as kilopascals because it's easier than quoting that 10 to the 5 all the time. Be careful to convert to the 10 to the 5 version if you are doing calculations where you want it to come out in newtons per meter squared. Using kPa will have you out by a factor of 1,000 in your final answer. I personally like units such as bar and atmosphere. Being a bit of a atmospheric scientist, in fact, a lot of my work was on the atmosphere of Mars, the bar was quite a nice value. 1 bar being Earth's atmospheric pressure. That unit tends to be out of use in terms of calculations, but you often find atmospheres and bars quoted in a lot of places, especially where there is civil discussions about the weather. So the cause of the pressure change with altitude is actually how much air is above your altitude, how much air is above you. And the higher you go in Earth's atmosphere, the less mass of air is above you. So we end up with more pressure when we're lower down, simply because there's more air above you pressing down on you. So let's look at a problem involving this. Let's calculate the pressure at an ocean depth of 1,000 meters, so 1 kilometer. We're going to assume the density of seawater is 1.024 times 10 to the 3 kilograms per cubic meter, and that pressure of P0, this remember is sea level, is going to be 1.01 times 10 to the 5 pascals. So what have we got? We've got a height of 1,000 meters, a density of 1 times 10 to the 3, and a surface pressure of 1 times 10 to the 5. And we want to find the pressure at some height. So this is always a good idea to write out your variables that you have. So the height we want to find that is 1,000 meters. We know this. Here's our density, here's our surface pressure. What's the pressure that we want? You know what you want to get to, you know what you have. So if we want to find P, we can use these variables to lead us to the equation we need, which is P0 plus rho times G times H. We have all these variables. We're going to say that we're looking at the pressure at sea level plus our density times G times our height. This essentially being our depth down in the ocean. So P is going to end up being 1 times 10 to the 7 pascals. That, if you look at it, is about 100 times greater than atmospheric pressure. Atmospheric pressure was 1 times 10 to the 5. We're now sitting at 10 to the 7 pascals. So this is an issue with things like submersible vehicles. If you take a submarine and you go deep enough, eventually that vehicle will be crushed by the sheer pressure of water that it's actually experiencing. The force per unit area will be too much for its structure to take. That's why we haven't actually explored the deepest oceans as of yet, as that's a more complicated engineering challenge than it is to, say, go into space, where the problem is reversed, where we have lower pressure outside the vehicle than inside the vehicle. And it always draws my eternal ire when TV shows can say, oh, well, spacecraft function quite effectively as submarines. That always shows me that the person writing that particular story has no idea. Another pressure you might see is referred to as gauge pressure. If something asks for a gauge pressure, what it's saying is what's the pressure from a particular device, such as a tire gauge. This will often be slightly different from atmospheric pressure depending on the calibration of the gauge. So a gauge pressure should always be considered as what is the pressure of the system minus P0? What is the differential from the actual pressure and the real pressure at which the gauge is functioning? So let's take a look at a few more examples. Here we're looking at a situation where we take our finger and we put it on top of a straw. If you do this, you'll see that inside the straw there is actually fluid. You can then remove that straw from the liquid and the fluid will stay inside the straw, when really, logically, you'd expect it to fall out. Remove your finger from the straw and the downward force from the air pressure winds up with the liquid falling out. So how does fluid remain in this straw? Well, what variables do we have to work with? We have some height h that the fluid is actually occupying. We have a length of our vessel and, of course, the density of the fluid in the straw. We have a pressure acting on the bottom here, and we have some pressure that's in the vessel between the fluid and the finger. Other things we have to consider. We have an area, and that is the cross-sectional area of this system. So the pressure on area A is going to end up being P, and this is going to be the pressure here. P down is going to be P plus the pressure due to gravity. So P up here is equal to PA, atmospheric pressure. On this end we have atmospheric pressure. On this end we have some unknown pressure. So P down is what is this P plus the pressure due to gravity. On this end we have atmospheric pressure. Now, if our fluid is at rest, that is not moving and just sitting in the straw, which it will be, it'll just be sitting here in a static case. When it's at rest, all of the forces in the y direction should equal 0. This means that the pressure upwards equals the pressure downwards. The pressure in the x and y directions in the positive and negative cases will be equal. So PA, the pressure here, the atmospheric pressure, has to equal P plus the pressure due to gravity, mg. So if we think about that for a second, P is going to equal PA minus mg, and this will give us a limit at which the fluid will be held in. So air pressure will hold fluid in the straw, provided that PA minus PMG is less than the atmospheric pressure. And this is what's referred to as Pascal's law. Any external pressure that's applied to a confined fluid increases the pressure throughout the fluid by some value of P. So if we go to the bottom of a lake or the ocean, this is what we will get. And we've already seen this result. This is just putting a name to it. P is equal to P0 plus rho GH. So if we're looking at density, we're looking at pressure, there are effects if we go very, very deeply of melting, boiling, freezing, condensing. We can add heat, we can remove it, we can add potential energy. If you're very deep in the ocean, it's actually quite cold, and this can affect the density. But we're not really going to worry about heat transfer in our cases. What we're concerned with right now are pressures. And looking at Pascal's law, here's a picture of Pascal himself with a very ornate sun in the sky behind him. Pascal's law can be expressed in the sense of the straw we were just looking at, in equalizations of pressure. So here, P1 is equal to P2, and that gives us, substituting for pressure, F1 over A1 is F2 over A2. And Pascal's law in words makes this statement. A change in the pressure applied to a fluid is transmitted undiminished through every point of the fluid and to the walls of the container. What he's saying is the container exerts a pressure on the fluid, and that force can be transmitted through the fluid. So that's what's happening when you put a fluid into a container. There will be a pressure inside that container due to its walls. Crush the can that the fluid is in, and you end up with the pressure increasing. Seriously, try taking a Coke can full and just squeezing it. Pressure will increase inside. It's also a very useful way of transmitting force, in that pressure is the force that's applied to a system over its area, and this is going to be equal to the force over a second area. So, in the particular case of this hydraulic press, here we've got a very heavy vehicle, and we want to lift it up. Here we have a small diameter pipe, A1, the area A1, cross-sectional area, and we'll apply a force F1. This will end up with the force being translated through the fluid and inflicting a force F2 here over A2 to lift this vehicle. So if we want to calculate what F2 is here, we can say F2 is F1 times A2 over A1. So if we're looking at a case of, say, the car lift, in this case, the car lift is using compressed air to exert a force on a piston of circular cross-section, radius 5 centimeters. The pressure is transmitted by a liquid to a second piston of 15 centimeters. So here we have a piston, A1 here. This area will have a radius of 5 centimeters, and this one 15 centimeters. And then we're applying a force, and that force is being translated through the fluid to this piston, pushing it upwards. So what force must the compressed air exert to lift a 13,300 Newton car? So on this end, we have a 13,300 Newton car. That's the force we want out. Part B says what air pressure will produce that force. So what air pressure do you have to put in here in order to get this force F2 out this end? So what do we know? Well, we've got two radii. We've got the cross-sectional R1 for the cross-sectional area of 5 centimeters over here. This is 0.05 meters. We've got an R2 over here of 15 centimeters. I immediately convert these into meters. We don't want a confusion anywhere. We don't want to be out by a factor of 100 in some way. So I immediately convert both of them before I even start the problem. Our force is 13,300 newtons. The question is, what force must the compressed air exert to lift a 13,300 Newton car? So what's F1 is what we're really saying. So we could go back to our equations from before. F1 over A1 is F2 over A2. rearrange them. F1 is A1 over A2 times F. Now the area, if we assume these to be circular cylinders, and as we're given a radius, that would be a reasonable assumption, we can say will be pi r1 squared over pi r2 squared. If we substitute in, this will be pi 5 times 10 to the minus 2 over pi 15 times 10 to the minus 2. I have squared these in the calculation, even though they're not present here. Multiply this by our 13,300, and we'll get 1.48 times 10 to the 3 newtons. Part B asked, what air pressure will produce this force? So we just calculated the force that we needed here of our 1.48 times 10 to the 8 newtons to lift this vehicle. Now we want to know how much force do we have to put in this end to get this force out. Our pressure is going to be whatever F1 is over A1. We know what A1 is because this is going to be pi times 5 times 10 to the minus 2 squared 1.48 times 10 to the 3 over 7.85 times 10 to the negative 3 will give us 1.88 times 10 to the 5 pascals, or newtons per meter squared, which would neatly come out of this equation if you're unsure of the units. And Pascal's law has many, many applications. Hydraulic brakes, for one. Anywhere where you are trying to translate a force around a corner. Here's a brake system. If you have this end attached to your brakes, you push the pedal here and this will push this cylinder, and that will use Pascal's law to increase the force at this end of the brake and push these pistons with a greater amount of force to squeeze the rotor and slow down your wheels. So this is basically how brakes will apply a greater force at this end than you're putting in with your foot. The same way, things like hydraulic jacks, here we're going to be using Pascal's law in order to exert a force on a piston. It's very similar to the situation we saw in the previous slide. And we could also be looking at a situation with things like forklifts, where we want to use some kind of compressed oil in a hydraulic system to lift a large load. So as we mentioned previously, the most pressure measurement devices that you'll see use something called gauge pressure, and this is P minus P0, some atmospheric pressure at sea level, and that's equal to rho GH, and that's what you can call your gauge pressure. There are many ways of measuring gauge pressure, from tire gauges through to aneroid gauges to manometers. Usually the physics behind this is something like a Venturi tube that we'll see later, or some other similar system. But this does lead to various pressure units. Pressure gauges use different methods to measure pressure. So an alternate pressure unit to rho GH uses liquid with some known density, usually mercury or alcohol in the case of something like a barometer, to measure height in a vessel. So what we deal with a mercury or alcohol barometer is you can look at the height of liquid and then basically put grades on the side of that tube and see the height of the liquid and figure out the pressure. This is why when you look at things like the weather being reported, they often still quote millimeters of mercury, even though it's a very outdated unit. And that gives the confusing case where quite often you can see pressure quoted in length units, because it's actually quoting what is the height of a fluid in a tube as opposed to what is the actual pressure that is being exerted at a specific location. So why do we bother to use mercury? It's kind of mean. It's not a very nice material. It's poisonous and is banned in most places. Mercury, it turns out, responds very well to pressure. We'll see that in a moment here. So for a height of 1 millimeter of mercury, this is 10 to the minus 3 meters of mercury. Rho, the density of mercury, and it is because of the density that mercury responds so well to pressure, rho of Hg, rho of mercury, is 1.36 times 10 to the 4 kilograms per cubic meter. Multiply this by G of 9.8 meters per second, and then we can look at the height of that fluid of 10 to the negative 3 meters. This will give you 133 newtons per square meter, or 133 pascals, or 1 torr. Millimeters of mercury in torr are not SI pressure units. We don't want to use those in any of our calculations. So, you might say, Dr. Horn, you mercurial polymath, why are you bothering to tell us about these units? The reason being that most of these units, thanks to a lot of weathermen and other people who refuse to give up their very archaic unit systems, are still quoted in places. Textbooks often use them. People who work in atmospheric science tend to use atmosphere and bar as opposed to millimeters or millimeters of mercury or inches of mercury even. We're going to restrict ourselves, if I'll give you anything, to pascals, or in maybe some cases, kilopascals, which you would have to convert. I will probably not give you any of these. But if you are looking around the internet at other sources, which I don't mind if you do, in fact, researching this material probably help expose you to as many problems as possible, other units are frequently quoted. So the atmosphere, abbreviation ATM here, is 1 times 10 to the 5 newtons per square meter. You can kind of see where that comes from. The bar, which is essentially same kind of unit here. Yeah, the abbreviation's bar. Millimeters of mercury, inches of mercury, PSI, of course, this one being oft quoted, especially when you're dealing with things like tires and engineering. Engineers refuse to give up their precious PSI, which is 6,893 pascals. So this is one you might see quite frequently. And then, of course, there's the wonderful torr. So these are very common. Even though I will try to restrict myself to pascals, you may see these units elsewhere. So in terms of a mercury barometer, as I mentioned, why do we even use mercury? It's because of its density. So when you see weather reports, they often quote the barometric pressure in terms of millimeters or inches of mercury. If we say something's about 29 inches of mercury, which is about where it sits for most atmospheric pressures, that's 76 centimeters or 760 millimeters. So if we look at 760 millimeters, that translates to a pressure of rho GH of about an atmosphere, 1 times 10 to the 5 newtons per square meter. If we try doing the same thing with water, because its density is so low, we end up with a situation where the height would be 10 meters or 30 feet. So if you wanted to have a nice, safe water barometer, instead of a mercury barometer kicking around your lab, you would have to have ceilings 30 feet high to accommodate it. It will work, but due to the lower density of water than mercury, that would end up with quite a large device. So enough about these things. Let's talk about one more example. Here we're going to estimate the mass of the Earth's atmosphere. If we're given the pressure of the Earth's atmosphere here at sea level of 1.015 times 10 to the 5 pascals, we'll need a couple of things to make this work. One being the radius of the Earth, 6.3 times 10 to the 6 meters. We already know that pressure is force over area. I realise that the Earth is not a perfect sphere, but we're not going to get into those tiny little corrections, so we're going to suggest that the Earth is an area of 4 pi r squared for a sphere. We'll ignore its oblateness right now. If we do this, the radius being 6.3 times 10 to the 6 squared times 4 pi will give us 5 times 10 to the 14 square meters. This means our force will be P times A. We can now say our atmospheric pressure multiplied by the area of the sphere will give us 5 times 10 to the 19. That still doesn't give us a mass. That gives us the force of Earth's atmosphere. At sea level, of course. Mass can be derived from F equals ma, where a, the acceleration on our gas, is going to be g. So m is F over g, substitute in, and we end up with about 5 times 10 to the 18 kilograms. Now, one of the things people don't like to hear about the Earth is that its atmosphere is actually bleeding off all the time. We're losing thousands of tons of Earth's atmosphere every second as it bleeds off out into space. Now, Earth has a lot of very heavy components in its atmosphere, which is why our planet still has one. If you're talking about something like Mars, which has a very low gravity, it's already lost most of its atmosphere and only retains the heavy molecules like CO2. So, even with this going on, at 5 times 10 to the 18 kilograms, Earth's atmosphere still has a long way to go before it bleeds off and leaves us with a lifeless, barren rock.